We're going to continue looking at applications of exponential functions in this video. In the previous video, we looked at an example of population growth, and we saw that you can represent exponential growth and decay in a real-life situation with this kind of equation. F of x is equal to a times b to the power of x, where a represents the initial amount of whatever you're talking about, b is the growth or decay rate, in other words, what factor you are multiplying by each growth or decay period. X represents the number of growth or decay periods, and that's important. The whole exponent represents the number of growth or decay periods. And f of x on the other side of the equation tells us what we're left with, or how much we've got after the growth or decay periods have passed. So let's look at another common example, radioactive decay. And here's a typical sort of question. Polonium-210 is a radioactive isotope with a half-life of 138 days. If there are 200 grams of polonium-210 at time 0, the first question is, what's the equation that describes the mass of polonium remaining after t days? So you start with 200 grams, how much is left after t days? Now, you have to understand the concept of half-life to answer this question. The half-life means that every 138 days, half of the sample disappears. So if you start with 200 grams, after 138 days, you'll have 100 grams. After another 138 days, you'll have 50 grams, etc. That means that the growth rate, or in this case, the decay rate, is written as a half. So our base is going to be a half. We also have to think about the number of decay periods that we have. So the half-life is 138 days. If we want to know how much is left after t days, we have to know how many half-lives have passed. If t days have passed and there are 138 days in a half-life, the number of half-lives that have passed are t divided by 138. If you had 21 days and you wanted to figure out how many weeks had passed, you would divide by 7 days in a week. Similarly, if t days have passed and you want to find out how many half-lives have passed, you divide by 138 because each half-life is 138. So this is the number of decay periods, and that means this has to be the whole exponent. Remember, the whole exponent represents the number of growth or decay periods. So the equation describing the mass of polonium after t days can be written as the amount as a function of t is equal to, so our initial amount is 200, our decay rate is a half, you're multiplying by half each half-life, and the exponent is t divided by 138. Notice the 210 didn't play in anywhere, it's just describing the mass of the polonium isotope. So it's a chemistry thing, we don't have to worry about it here. So that's the equation describing the mass of polonium remaining after t days. Again, the exponent, the whole exponent tells us how many half-lives have passed. If t days have passed, we have to divide t by 138 to work out the number of half-lives that have passed. Then we can ask how much is left after 2 years. Well, first we need to figure out the number of decay periods. Well, the number of decay periods is t over 138, and 138 is in days, so our time has to be in days as well. Well, 2 years is 730 days. So 730 over 138 is going to be our number of decay periods. That's going to be our exponent. So the amount after 2 years, or 730 days, is going to be equal to 200 times half to the power of 730 over 138. And I'd recommend that you leave all of this in your calculator to do it all in one step to get the greatest accuracy. And if you do that, being careful about your brackets when you enter it into your calculator, you get approximately 5.11 grams. So after 730 days, or 2 years, you're left with 5.11 grams of the original 200 grams. In the next video, we'll look at some more examples of exponential growth and decay.